Welcome back. Today we're going to talk about how straight runs of ductwork like this can change or alter a fan's performance when mounted to the fan's discharge. What we want to avoid is any loose articles like this lanyard or loose articles of clothing, rings, watches near a piece of rotating equipment. These items can get sucked into the fan inlet, get lodged into the fan discharge, or if we have shaft and bearings, V-belt drive or coupling, can get caught up on those devices as well. So the best thing to do, discard these items until after the presentation, and then you can put them back on again. For today's presentation, we have a fan, straight run ductwork, bell mouth inlet, pitot tube, some tubing connected to a magnet helix. This can give us a visual representation for how the fan's performance changes throughout the presentation. We have a straight run of ductwork, rectangular in shape, and we have a shorter rectangular round transition as well. It's demonstration time. But before we get started, let's talk about fan housings and how air discharges a fan. Fans typically have a volute-shaped housing, or a housing that's constantly increasing its radius. Air has mass. That mass wants to go in a straight line. As a result, most of the air hugs the outside of the volute shape. And we can demonstrate that by using this piece of paper. Putting it on the outside of the volute shape, that piece of paper stands up vertically. Put it on the inside of the volute shape, it actually gets sucked into the fan just behind the cutoff sheet. There's a negative pressure region there. To straighten out that velocity profile or get some static pressure regain, SMACNA, AMCA, most industry standards require or request a straight run of ductwork. And looking at the straight run of ductwork, there's nothing inside of it, just clean, open duct, nothing there to forcibly change the velocity profile. Put it on the outlet, and we notice that that velocity pressure measured by the magnet helix has gone up pretty substantially. And that's because we have static pressure regain in this piece of ductwork, and we're allowing the velocity profile to even out. What do I mean by an evened out velocity profile? Well, if I put this piece of paper on the outside of the volute shape, it still forcibly is stood up. However, if I put it on the inside of that volute shape, it's still forcibly forced up. It's no longer being sucked into the fan just like it did behind the cutoff sheet. Now, you need a piece of ductwork, but how long do you need it? Well, even a short piece of ductwork, you're going to get some regain. And we can show that by utilizing the smaller, shorter, rectangular round transition. Put it on the fan outlet, and we can see our velocity pressure went up. Not quite as much as it did with the straight run of ductwork, but it still went up pretty sizably. Velocity profile, put it on the outside of the volute shape, stands up the piece of paper. Inside of the volute shape, that piece of paper stands up pretty substantially as well. So you can see that even in this short distance, the velocity profile evens out substantially. Thanks a lot. Let's move on to final thoughts. Ductwork on the fan outlet has a pretty big effect on how the fan performs, just like ductwork on the fan inlet. You need to have an effective duct length in order for that velocity profile as it discharges the fan to even out and get static pressure regain. AMCA standard 201 shows or tells us that we need to have 2.5 duct diameters for the first 2,500 feet of velocity, an additional duct diameter for each 1,000 feet of velocity on top of it. It also shows in the graph or the diagram that if you have 50% of your effective duct length, you're going to get about 80% of your regain. So if you have an obstruction or some reason why you can't utilize full length of duct, something is much better than nothing. Thanks a lot. Any questions, comments, put it on the section below. Any thoughts on future presentations you'd like to see us do, let us know as well. We'll get right on it. Thanks.